Well, thanks so much for coming out. This is pretty fantastic. It's, so we're going to chat a little bit about weather, and we're going to talk about it from the perspective uh, of paddlers, but really it's really anybody in the outdoors doing stuff outside. And I find that when people think about weather or try to, it's a really complex topic. And so tonight is we're going to try to dumb it down as much as we can. My warning right from the start that I always give to people is you're definitely not going to become a meteorologist out of this. People actually go to school for this. So we're going to try to keep it real simple tonight. And so, but yeah, so let's talk, let's chat a little bit about weather and kind of figure out what's going on upstairs and some forecasting. So what are we going to do? We're going to talk a little bit about what's going up there, weather observations and short-term forecasting, and kind of how to set yourself up for that. And what are some signs of, what the weather's going to do over the next 6 minutes, 10 hours, 24 hours type thing. We're going to talk a little bit of lightning safety, and then we're going to finish off. We're going to talk a little bit about wind effects over water. So it's not, it is weather related, but wind does really weird things on water. And so we're just going to chat just briefly about that kind of right at the end, rather than ending on the chilly, scary topic of lightning. We'll talk about wind at the end. So as paddlers, when we think about weather, we're mainly interested in a couple different parts that we really want to pay attention to. And so we really want to pay attention to wind direction, temperature, wave height, and precipitation. And so when you're listening to a weather forecast, they cover lots of different topics, but really when it comes down to it, it's, what's the wind speed and the wind direction? Because, are you going into the wind, or are you going downwind, or is it going to blow across the bay, or is it coming off the land? So wind direction is a big thing. Temperature is important, mainly related to, what clothing you're going to wear, and, what's the day going to be like. And then hooking off the wind side of things is with the direction is how big are the waves going to be? And then obviously, is it going to rain or not? Of the four that we are going to want to really think about, it's all about wind, and especially in the wind speed and wind direction are kind of the big things, because whether it rains or it's cold or warm, you can accommodate for those types of pieces. So those are kind of, when you really boil it down, that's what we're interested in. So when we think about weather, there's a huge swath of topics that are out there, but there's three big kind of zones in a sense. There's kind of global weather, or weather patterns that affect half a continent all the way around the world. So we're going to talk just a little bit about some of the big global stuff. Then there's regional weather, stuff that might affect something that's a half state or a full state or half the province big, and then different types of weather that affects us locally at our campsite, but maybe not at the other end of the lake. So what happens when it rains at our end, but not at the other end? That's kind of what we're getting at there. So we'll kind of drill down. But we'll start with things at a global level, just kind of giving you a bigger picture of what's happening out there. And then we'll get down into some of the real practical type of stuff. So what causes weather, or what's the biggest single piece that contributes to weather on Earth? And it really comes from the sun. The sun puts in a massive amount of solar energy, and when it hits the atmosphere, that turns into thermal energy. And it's the thing that really is the engine that drives weather on our planet. And when you've got a combination of, since the Earth is spinning around and you have big continents and big bodies of water, you get what's called differential heating. And you get these masses of cool air and warm air, and that heat up at different points. So the air over the land heats up faster, air over water heats up slower. So, and then on top of it, the Earth is spinning around. And so you've got a lot of stuff that's happening, but heat, generally, when you really boil it down, it's that we have parts of the Earth that are hotter than other. And so air travels all around to try to cool and balance that out, but it can't, because the Earth is spinning and the sun just keeps putting more and more energy into it. Okay. So when it really comes down to it, this is a major factor in kind of what kicks the engine going. There's other things as well, but look at that happy sun. That's really doing a lot of work for us. Okay. This differential heating leads to air traveling around and moving and circulating in semi-predictable patterns at a global level. And so we're going to zoom way back here. And so what happens when air heats up? It gets hot and it rises. And when air gets cool, it sinks. Okay, so if we go off that piece, you can see that there is the air over the equator. In theory, it's kind of one of the hottest bands around the Earth, and it's got a lot of moisture in it, so it rises up. And when it heats, it cools down and condenses and rains back down. So you tend to get a lot of bands of equatorial rainforest is very common in this part because of the high moisture. So the air is traveling up and it hits the top of the atmosphere or the troposphere. And so it has nowhere to go. So it travels across, some goes to the north, some goes to the south. And as it travels north, it gets cool and starts to sink again. So what you get are the cell of air. And if you think of it, it's kind of like it's a band that goes all the way around the Earth in the cell, and air rotates in a fairly predictable pattern in the cell. If you go up a little bit further up into the latitudes, then what you've got is another cell. It's just called the Ferrel cell. The name's not important for what we need to do, but the concept is the important part. And so what you get is up around the Great Lakes, or here in Ontario where we are, or most of us, some of us are, is the same thing happens. And so you've got this hot air that starts to rise and it condenses and grains, and some of the air goes to the north to the poles, and some of it travels around, it cools down, but then it falls back down over the southern area, and it tends to be really dry, cool air. So that's why in at least kind of the first half, like California, you get a lot of deserts in that particular region. That's kind of one particular factor here. So the air is coming in. Long story short, what we have are three big, at least in the northern half of the planet, is we have these three big cells. So the Hadley cell, the Ferrel cell, and the polar cell. And so what it is it's air that's rotating, generally stays within the cell. There's a little bit of spillover, but not much. And you tend to have moist air that's rising, cool air that's falling. And in between those is the band way up at the top. In between those, you have the jet stream. And you might have heard of those that before. I'm going to talk about it just a little bit more. But it's kind of a really interesting piece. And this all happens because of differential heating. And this thing keeps going because the Earth is spinning. It can never really balance itself out because it's hot and cold. And the land is heating up when it gets in on a sunny day and cooling down at night. So there's all this interesting stuff that's happening. But how does this play out for us? So here it is looking straight down. And so you've still got your three big bands that are spinning around, and you can see they're kind of, well, my poor arrows here is kind of simulating that it's spinning around. And so what this leads to for us is their trade winds. And it's generally, the trade winds are just the general direction that weather and wind tends to blow the majority of the time. And so at our level in the Great Lakes, it tends to come from the southwest. And there's wind will blow from all the different directions, depends on whether the storm coming in, but generally nice days, wind is coming out of the southwest, and our weather tends to come from the southwest. So in Toronto, we used to look to Chicago and say, okay, what's coming in the next day and a half? And that's generally where our weather would have come from. And that's because of these kind of big tubes or cells of air that's coming along. You can see the boundaries between that is the jet stream. And the jet stream is just another piece of high traveling air, or really fast traveling air at the very upper level of the atmosphere. And they travel, and they essentially is what moves giant weather systems around on the Earth. And it keeps going, and part of this differential heating keeps that jet stream moving along. So that's a super boiled down version. There's obviously a ton of more science into that, but really we just want to kind of emphasize that the trade winds and the direction of wind coming out of it is because of differential heating. And air gets in these cells, and they just kind of spin around around the Earth within their own individual little cell. Okay, so there's more big global type of stuff, but let's drill it down to something that's a little bit more practical for us. So let's get into some regional weather and different kind of weather patterns that affect things at much more regional, so all of southern Ontario or half of Minnesota type weather. And this is where it gets a little bit more interesting. Certainly for me, that other stuff's interesting, but there's so much science and I kind of blow through it quick. So the big thing that affects is at the ground level for us is we talk about high and low pressure systems. And you've probably heard people talking in, we got a low pressure coming in tomorrow, or there's a high coming in for this weekend. So it's going to be hot and sunny, like the weather people do. And that's what we've got here. And so high and low pressure systems are essentially different types of air that has similar temperature and similar air pressure, likes to group itself together. And the amount of moisture that's in generally, yeah, okay, so that's, I kind of got distracted. My family's walking to the door. And so I got distracted by them. So what you got is a high pressure system, and in other plots, you've got low pressure systems. And the high pressure systems, let's talk about those a little bit, and then we'll talk about low pressure systems in a second. So generally, they tend to be nice weather, cool, dry air is the easiest way to describe that whole thing. Where low pressure systems are the opposite, where you tend to have warm, moist air moving into your system or into your area. And low pressure systems is generally where we're going to find cloudy, rainy days. You can think about that. And so because these are different temperatures and different amounts of moisture and different pressure, they tend to not really like to mix a lot. They'll flow into each other as you can see by the arrows, but they do tend to be these distinct, generally these distinct different air patterns, okay? So high pressure systems, they tend to be your kind of classic, cool, really clean days, blue skies, not a lot of wind, awesome summer days. In the wintertime, they tend to be really cold days because the air is cool. And in the summertime, it still can be really warm, but it tends to be cool, dry air. But because there's not a lot of clouds, you get a lot of sunlight, so it feels really hot, okay? These arrows that are in this screen they're the wind direction. And wind spins off a high pressure system always in a clockwise rotation. And if you think of it kind of like a hill and someone's skiing down the hill, they're going to start at the top pretty slow, and they're going to ski and they're going to ski and they're going to get out of control, and they're going to get faster and faster as they get to the bottom of the mountain. And this is the exact same scenario. So the winds are really slow in the center of the high, and they're faster as they get to the outside of the high pressure system. So as a high pressure system starts to move into your area, you're going to get high winds on the outer edges of it. But then as that H starts to slide over top of you, you'll find that the wind dropped way down, and it's just really nice, warm, windless days. You've all experienced those out on the water with not a lot of wind, and that's exactly what's generally happening. But then as the backside of that high moves out of the area, the reverse happens, that the wind starts to speed up because the outer edges of the high tend to have the highest winds for it, okay? The low pressure is exactly the opposite, exactly the same, but completely the opposite, in which case the middle of the system has the highest winds and the most intense part. So we think about that as a storm, and the outer edges of the low are windy, but almost the very center of the low is got the highest speed winds. So if you think about water going out of a toilet, it's kind of a great little example of that. Just about as it's supposed to leave the bathroom or the toilet bowl, okay? And it's the same thing. So when a low pressure moves into your area, you'll find that the closer you are to the center of the low, the stronger or the most intense the weather is going to be. And then as it leaves, it slowly edges its way off. A low pressure system, we associate it with poor weather in the sense of cloudy, stormy, and there's some factors we're going to dive into below in a second. But if you'll see it's got lower pressure, and if you had a barometer, you could see that the air pressure is lower in the middle of it. And if it gets really low, a low pressure could just start off as a storm, but if it gets more and more intense, say the winds, the high pressure is feeding into it, it could turn into a hurricane, and where it's just a super deep low, a really intense storm is essentially, that's what our hurricane is moving into an area. And you've seen the little animation of the counterclockwise thing on CNN when some guy's talking about it. So that's a little bit about high and low pressure systems. And so they're really an interesting piece. And because they don't like to mix, we talked about they bang into each other. And so highs will move into the area and they'll bang, and like billiard balls on a table, they'll bang each other around. And this is part of where you get this chaos effect and why weather is hard to predict, because while wind can move in a general pattern, how they bang into each other and how they shuffle around is a tricky part to predict for that. All right. So let's take a deep dive into low pressure systems, because high pressure systems it's stable air that it's not really chaotic. Low pressure systems is where weather and intense systems are really chaotic. So this is a low pressure system, and in between that, you've got different boundaries of air masses. And so you can see one there. Because this thing spins in a counterclockwise rotation, it's going to pull up warm air from the deep south. And I'm talking mainly from kind of an Eastern Canada perspective. The same concept happens in other parts of North America, but to different, the Rockies kind of mess this kind of classic pattern up a little bit. So you can kind of step past that just a little bit. So this thing's spinning around and it pulls up an air mass from the deep south. So it's hot, really moist air. And that would be, you get your hot, super hazy, muggy days you've all experienced that in summer, but it's also pulling down cool, dry air from the north. And these two, where we talk highs and lows, don't like to really mix together. Within a low pressure system, different air masses as well don't like to bang into each other. They're very sensitive to it, and it takes a lot for them to mix. And where they bang into each other is called a front. And so you've got a boundary between these air masses, and this is a cold, prickly shape of triangle, is what's called a cold front. And then there's another one up here separating these two air masses, the cold air and the warm one, is called a warm front. And I'll talk about the two of them in a second, but that boundary between those air masses, when that boundary passes over your area, that's when you get intense weather. That weather transition is the big thing that between the different air masses is where you're going to get your storms and your excitement. Well, if that's what you're after. Okay. So what's the difference between a warm front and a cold front? Well, or how do you know which one's coming in? Essentially, the air mass that's pushing out the other one is what it's going to be named after. So where we've got warm air here, this thing's going to spin around and cool air is going to come in. You're going to have a cold front. Up above the low, where you have cool air already here, and this thing's going to spin around up over Algonquin Park, you've got a warm front coming in. And that's the easiest way to remember. So what's the air mass moving into your thing? You're either going to cold front or warm front, but how they present themselves is completely different. And this is what, when you start to get on a trip and you're 3 or 4 days into the trip, you start to see this type of stuff happen all the time. So what we got here is a warm front. And so what you have is, this is a real textbook example, and you would have all seen this 1,000 times, and maybe you've noticed it and maybe you haven't really paid attention, but you'll certainly notice it now. So this is what a warm front looks like when it's moving into our area. So we've got this little tent that seems to be hanging out here, and it's got cool, dry air sitting above you. And so it's got cool air, and warm air starts to move into the area. And so it travels slow, because warm air travels slower than cold air, because it's, hot and tired, and that's the easiest way to think about it. And what happens is the air, as it comes in, it starts to ride over top of the cool air. And that's essentially just because the cool air is cold and dense. So the hot air just kind of comes in and rides above it. And so that boundary in between the warm air and the cool air is where you start to get these clouds that start to come in. This whole process moving into your area can take anywhere from 12 to 36 hours. 24 is kind of the typical thing. So as this air mass comes in, if you look straight up, you start to get really little tiny whispery clouds. It starts to move across your area. So those clouds start to get a little bit bigger and lower. And eventually the clouds get darker and bigger and lower, and they're right on the ground. And then you start to get rain as it starts to move in. The boundary moves out of your area, and as you look up, and all of a sudden you've now fully got, you're in on the other side of the boundary. So you're in a group of warm air, and it tends to be gentle winds, but a rainy day, okay? But it's preceded by these clouds. So when you start to look up and you see little whispery clouds, then later in the day, they're grouping together and lower down. And that trend keeps going of grouping and lowering. You can say, okay, it looks like there's a warm front moving into our area. And so it brings, you're going to get some cloudy, rainy days, but probably 24 hours and the system's going to move out, but it's not going to be super high turbulent winds that a cold front is. Okay. Does that make sense so far? Holler if you've got any questions. Dan, pipe up if people have got questions. Okay.
No, so far it's just been very informative, and everybody's glad that it's being recorded because there's a ton of information.
Ha!
So there was
whatever you do, don't try to don't research anything more, because then you'll realize I'm making the whole thing up.
Well, yeah, and there was one note on one of your diagrams. Your trade winds and your westerlies are flipped.
Okay.
Just as a heads up. Yeah. Outside of that, love the animation.
I'm not definitely not infallible. Okay, so that's a little bit about warm fronts. And so if we go back to the slide, this is where our tent was at the A, and what we have is warm air starting to move in, and that's just because of that rotation of the low is pulling in and sucking that warm, moist air into your area. And so for us in the northern hemisphere, when this happens, the low is always south of you or southwest of you, and it's just because of the way that the thing rotates through that you're going to get that. And so what you have is on weather maps, this used to be a bigger deal. It's not, they don't really display it quite the same way anymore, where you have a red line. And I couldn't draw half circles, so it's full circles in this one, but usually it's like half circles for it. And then the cold front has got prickly side of things. So let's take a look into that, because that's where things are really interesting. From, if you're into storms and wind and lightning, cold fronts is where to be. That's where the cool kids are. So if you've got warm air already sitting over your tent, and all of a sudden cool air starts coming into your area really fast, you're going to get cold front. And that boundary is where the excitement is. Okay. Usually it's that kind of quick transition between one air temperature to the other is where it is. And so here's this coming in. You've already got warm air. Cool air starts rising in. And so what does it do? It drives, because it's more dense, it drives that air up into the atmosphere, that warm, moist, which is the key part. And what does it do? It starts to condense. So now you've got these huge big clouds that are building up, kind of being wedged ahead of that cold air mass. And so because it's building super fast and condensing really fast, you're going to get really big storms right underneath that. Cold air moves really fast into an area, because you're cold, you run around, you want to keep active, and the air is the same way. So because it wedges in really quick, you get this really intense half hour, 20 minutes, 45-minute storm, and then the boundary has passed you off to wreak havoc somewhere else. So, but then as soon as you're on the backside of that cold front, because you're in that new group of air, what does it feel like? You would have definitely experienced it. And it's where the humidity breaks, and it's way cooler on the other side. All of a sudden, like, it's gone from, 80 degrees or 30 degrees Celsius, and the humidity, it's now hardly anything. It feels really cold. And that's exactly what's happened right here. So that little tent right now, you'd be in that tent sweating like crazy. This huge storm comes flying through, and really got high turbulent winds, so it leads to lightning, which we'll talk about in a sec. But as soon as that passes, the humidity is broken, and the day is awesome, and it feels super fresh. And that's cold front. Okay, so in our last time, and then we're going to move on. So that's exactly what happens. Is the tent was on this side of it, the line passed over, and now air is sitting on top of you, and you've got a cold front. So this type of weather systems, these low pressure systems like this, that can be spread over an entire half of province, or it could actually be really small, and it can be a micro size. So this is partially why you might get rain at one end, but not at the other end of the lake. But this tends to be all of Southern Ontario experiences this. And you've probably heard them talk about, a storm front is moving through, or high winds, like a warning type system. That's exactly what's happening. The air masses, a cool air mass is being pulled into the area, and it's just sweeping all that humidity and moisture out. Let's see what's next. Let's get drill down even more, and let's talk about the local weather that affects us. And this is kind of where we start to get really practical. So the other stuff's good to know, because you want to impress your friends. But let's get into talking about stuff and kind of weather forecasting of kind of what's happening right above us. So if you want to know what's going on upstairs, clouds is really the secret to it. And a lot of stuff can be figured out basically just by watching clouds and seeing trends is the big thing. Okay. So there's a lot of science behind clouds, obviously, and there's a lot of names for clouds, and there's tons of different variations. But if we boil them down, there's 3 different types of clouds, 3 different types, and there's 3 different heights of clouds. So, but within that, there's lots of different stuff. But this is kind of the stuff you see all the time. So the first one is cirrus clouds. So they're the wispy little clouds that you tend to see really high up in the sky. People call them mare's tails, or look like hair. The next ones you see is cumulus clouds. They're like a heap or a pile, a clumpy cloud. The name's not important. The concept is the important part. And the last one is stratus clouds. And that is like a sheet-like cloud. So it's stuff that's covering the whole stratosphere, and you get the stratus clouds. So as I mentioned, there's generally 3 different levels where our weather sits in the atmosphere. And you got upper level clouds, you got mid-level clouds, and you got low-level clouds. And the shapes are similar, but how they behave is slightly different. And that has to do with mainly that some is water and some is ice, and that type of thing. So in the upper level clouds, it's stuff that's, hey, let's just back up here. Okay, so upper level clouds is 6 kilometers up, or 6,000 meters, or 20,000 feet. That's generally where that kind of upper level zone, and it keeps going up from there. So what have you got? You can get all 3 types of clouds up there, but they're all ice, because this wave, it's super cooled air, and it's at the level that jets fly. And so when they're coming out, all their hot moisture that's coming out of the engines, it turns into those contrails because it just freezes and turns into crystals, which is what you see. So you've got the little wispy cloud tendrils that are up there, all kinds of cool stuff. You get these layer clouds, which are kind of neat. Mid-level clouds is kind of 2,000 meters, or 6,600 to up to just below the boundary of 2,000 feet, 20,000 feet. And then we got low-level clouds, which are down at the ground level. I'm going to ignore this big giant guy for a second. So what is upper-level clouds, and what do they tell us? So yeah, generally, what does that tell a paddler? Get out, enjoy the day. When you see high-level clouds like that, it's not going to rain in the very short term. Okay. Of course, as soon as I say it, there's going to be an example of where it has, but we're talking very general sense here. But we learned earlier about a low warm front moving into our area, that big kind of wedge shape. So at the very front of it are the high-level wispy clouds, and that's what you're seeing. So you could expect it when you see these. It's a bit of a forebearer to something that could be coming our way. Sometimes it blows through, but if you start to, it's the start of the trend. And so expect a change in the weather in the next 24 hours is kind of a typical thing. And so, but but today it's going to be awesome. So get out there. There's kind of a little quick example of some upper cirrus clouds. Mid-level clouds. And where you've got here is you've got clumpy clouds. And in the cloud world, people who are cloud scientists, I'm sure they've got a name on their business cards, but I don't know what they're called. Cloudologist or something. I don't know. But anyways, what they do is they take, they add prefixes and pieces to the end of it. And so you've got here is altocumulus or altostratus. They'll add the word nimbus to the end of certain these clouds if it's dark and scary. But the names, again, is not important. It's the concept. So if you start to see clouds up at high level, Now you're starting to see clouds at a lower level. You can see they're starting to clump together a little bit more, or maybe even start to spread out across the whole stratosphere into stratus clouds. So what's this telling us? So it's basically you've now connected the dots and you've got a trend of a warm front starting to move into your area. Okay, so unstable air is coming, and now you're looking at 12 to 18 hours is weather change, typical. So you can look at this and you start to see these clouds at night, and they look awesome at a sunset. They're like fantastic for photos, but you starting to think, okay, well, tomorrow morning it's potentially going to start to rain or a change in the weather of some type. At the low level clouds, this is where now the clouds are really come together and they're lower. They're all water, as opposed to in the mid and the upper level. They can be a mix. The upper level is all ice. The mid level is kind of a mix between water and ice. This is all water. This is where you're going to get your rain from at this thing. So what's happened to this at clouds at this low level? Well, we already know it. You look outside and you're just going to think, oh, I should bring an umbrella to work, or I should put a tarp up. Okay. So what you've got are some stratus clouds. You've got a solid rainy day. You got big cumulus clouds. It doesn't always rain under those types of things. And then, of course, at the ground level, you got fog. We're going to talk about the cumulonimbus in a second. All right. So the big thing about weather forecasting is you can take a snapshot right now and you could probably make a prediction of what's going to happen in the next hour. But if you really want to think about what's happening over the next 24, 36 hours, you have to think about looking back in time. So what did I see and what were my trends? And that helps give you knowledge to project into the future. Okay. So when you first jump on the water, even before, is take a snapshot of the sky. So what does it look like? Where are the clouds and how high and how clumpy? And then at lunch, do the same thing. So have they changed from what I saw in the morning? And at the end of the day, it's the same thing. So now you've got 3 observations you can now predict with much better accuracy than just guessing. Okay. So that's about low level clouds. Let's talk about cumulus clouds, because they're an interesting piece because they look awesome. Those big puffy clouds you see. So what's happening here is what happens, clouds condense because essentially what they are is it's hot air that's rising with moisture in it, and it gets to a certain point and it condenses and just sits at a point in the atmosphere. And so if there's enough moisture and enough heat, it's going to get bigger and bigger and bigger and turn into one of these big giant puffy clouds. If the air around it is really dry air, it's going to try to absorb that cloud back into the atmosphere. So there's this balance between moisture in the atmosphere and how much moisture is coming into it because of a farmer's field or off a lake. You get these kind of big, giant, puffy clouds. And the denser the clouds get, the scarier the underside looks because the light can't get through. So if you take a look at this guy down here, it's just really dense. And you've seen that all before. So you get a sense of kind of, are you going to get rain from that or not? It just, it becomes a bit of second nature, and you're at that level already. Eh? Clouds are also interesting because these keep separated clouds form because of rising air, but then cool air has to displace it because you get this cycle of rising and cooling air. So air comes down and punches these clouds apart. And so that's what kind of keeps them separated. Eventually that cycle breaks down, and that's where you get stratus clouds, where it just fills the whole atmosphere, just because there's not enough heat anymore to kind of keep that up and down air going on. So let's talk about the big scary one, cumulonimbus, which is just a cumulus cloud that's gotten scary because they add a nimbus at the end of it. And when you see these, and this is why we talk about them separately, because when you see these guys, these are the things that you really want to be taking care of and getting off the water. So you've got weather coming into your area within an hour, even minutes. So you need to get off the water. So what happens inside one of these clouds is you got, it's just a big giant balloon. It's kind of the easiest way to think about it. Heat and moisture is going into that cloud, but there's so much heat and moisture that it builds and builds and builds and inflates all the way up to the top, and it hits the top of our level of atmosphere, and it has nowhere to go. So it's kind of like smoke on a ceiling. It just kind of spreads out, and you kind of get that classic anvil shape that big clouds have. If we back up, oh, this one doesn't have it, but if this one's still building. So within that, you've got all this air that's rushing up and down within the air column, which creates static electricity, which leads to lightning. So these are the clouds that you really need to pay attention to because there's so much energy in this cloud bomb thing. It's both going to be a really turbulent wind, high chance of lightning, definitely going to rain head to shore. Okay. These things blow up really quick and they fall apart just as fast. And so you would have seen these storms come through, and there's enough heat, enough humidity to create these little mini storms just at your end of the lake. And then they're very unstable. So they fall apart super quick, or hopefully they rain on someone else and not on you. Okay. But when you see this stuff start to build, you should be thinking, we need to think about head to shore just because of the risk for it. So here's kind of one blowing up. Look at that guy. You see it's hit the top there and now it starts to spread out. And underneath that, it's still pouring more and more wind into it. Watch it one more time. So this would be, it gets cut off a little bit early, but sometimes they turn into huge big storms, as you know, and sometimes they don't. And this particular one, probably about 15 or 20 minutes, probably gotten even bigger and probably started raining at somewhere along the way because it gets really unstable and just collapses in amongst itself. But they build up really fast. This is probably a span of within 10, probably 15 minutes. But what we've got here is a really hot day, a lot of moisture coming off the ground or off the lake. And that combination is where you get these types of storms that blow up. So how do you know if it's going to turn into that? And like I said, it's a combination of lots of heat and a lot of moisture. And when that combination happens, you're going to get a good chance of intense weather. And so here in the Great Lakes area, we get this a lot for sure. Hot, hazy afternoon, you're definitely going to, shouldn't be surprised when this happens. But if you're in a case where you have a lot of heat, but not a lot of moisture, this storm intense weather doesn't happen to the same extent. So somewhere that's really hot, but really dry, that would be the desert. It doesn't get thunderstorms from this type of piece. It might blow up into big pieces, big clouds, but it doesn't have that same level of intensity. Just like if you switch it around, you can get the same thing. So somewhere that has really high moisture, but not a lot of heat, doesn't get a lot of thunder and lightning storms. So rainforest would be a good example of that. They get lots of storms, but they don't get that really punchy, high winds, lightning storms. Vancouver doesn't get, or Vancouver, Victoria, or Vancouver Island hardly gets any lightning from that perspective, just because it doesn't have that kind of perfect combination of heat and moisture. So let's talk a little bit about signs of an imminent weather change. You need 4 pieces. Wind. So how do you know if a big storm is going to come your way? It's going to change real quick. Wind is going to be a big factor for sure. And that's increasing wind and changing direction. Those are big ones. You're going to see an increase in temperature. You're going to see a decrease in air pressure and the clouds. So we got that, we talked earlier, kind of clouds coming together and height of clouds dropping. So these are kind of your 4 kind of classic pieces, though it's hard to tell temperature without a thermometer, and it's hard to tell air pressure without a barometer or an old man to complain about his knees. So these 2 here are really invaluable if you have the equipment, but these 2 here are more valuable for us as paddlers because you can see it and observe it right away. And of these 2 things, wind is the big factor. Wind is going to be your telltale sign that something is going to happen. Just before that big storm really starts to move in, the wind is going to pick up because it's blowing into that big giant cloud. It's going to pick up and it's going to change direction. And even within wind direction is more important than even wind speed. Okay, so if you're paddling and not paying attention and all of a sudden you realize the wind direction has changed, it's blowing on one cheek and now it's blowing on the other, something has caused that to happen, unless you're going near a big cliff, you know, like something physical. But if it's just all of a sudden it's switched around on you, something's happening upstairs and you need to really think about what's going on. Okay, so pay attention to clouds, really pay attention to the wind, especially the wind direction is a big factor. Okay? So that's stuff that's going to happen in like 15 minutes. So these are the is wind direction and wind speed. Okay. Let's talk about lightning safety. Okay, where does lightning come from? What happens is you got a cloud and you have positive ions at the top of the cloud and negative ions at the bottom of the cloud. And those negative ions are trying to ground down to the earth. I'm boiling down a ton of science into this one to kind of make it really simple for us at this time of night. What happens is they've started to discover over the last bunch of years is lightning doesn't just purely just strike. What happens is it's a combination of these little tendrils of positive ions coming out of the tops of points from the earth. And so they're trying to get to the clouds while the negative ions are trying to get down at the same time. And whatever one ends up kind of winning the race and connecting is where the lightning is going to strike. Okay. This is part of the reason what makes lightning super unpredictable and why lightning doesn't always strike the tallest thing all the time. The tallest thing is kind of always got an advantage because it's closer to the cloud to be able to make that. So statistically, tall things tend to get hit a lot. But, you know, a short cow can get hit when there's tons of tall trees all around it. And this is just because the tendril coming off the cow's head is the one that won the race. Notice I didn't talk about the camper that got hit there with that lightning. Okay, so when you're thinking about lightning, you really need to pay attention. There's lots of risks to us that are really common, like driving is a really high risky activity. But lightning is one of those ones that you really need to pay attention to, especially in the outdoors. And the problem is that there's really no good place to go in the outdoors that aren't outside of going inside somewhere. So let's talk about some bad places to be and some less bad places to be. That's kind of how we think about it, because being outdoors in a thunderstorm is just a downright bad spot to be. So super dangerous places to be are kind of the big obvious ones, you know, the tops of mountains. So in the mountaineering side, this is a big issue for people who hike in the hills, because where are they going to go? So, you know, tops of hills, underneath the big tall trees, those are super bad spots. Look at this canoeist out here in the middle of this lake. Super bad spot to be in the middle of a thunderstorm. Okay, wide open area is a bad spot. Less objectionable alternatives. I work for government, so we're all about trying to come up with fancy terms like that. So what's the least objectionable places? And so it's like, it's not that they're better, they're just less bad. You know, so, you know, you're, instead of being up here, this is a better spot to be. In amongst trees is better, but it's still not great. In a gully is still not great, because in lots of places in gullies, you have issues around flash floods. You have issues around water and electricity traveling through water. Things like that are some of the other things why that's generally not a great spot. And then the safest spots you can see here is in a car or in a house. So yeah, those are really your best spots. But, you know, we don't have cars and houses when we go out in the out in nature. And so you need to kind of really think about when severe weather comes in, you need to think about, okay, where can I go? And it is very much a crapshoot and trying to sort that out. But get into and amongst trees and getting out of areas, getting low in low-lying areas is a good spot to go. But yeah, it's for people who have never experienced being in the middle of a thunderstorm, enjoy it, because it's pretty scary for sure. We use the 30-30 rule in the outdoor industry when we talk about when should I get off the water? That's always a big question. And this is your answer. So when you see lightning and you can hear thunder within 30 seconds of each other, you need to be off the water. Likewise, when the storm passes over and the last thunder you hear, you need to stay off the water for 30 minutes. Okay, so if you see a storm coming your way and it's you see the lightning and hear the thunder and you're within 30 seconds, you should be getting off the water, because you're in the danger zone. We'll talk about it in just a quick second. And then you're off the water for 30 minutes. And the reason is because lightning, so in this range of 30 seconds, that's about, for kilometers, it's about 10 kilometers away. That's within 30 seconds. So roughly the storm is 10 kilometers away. And there's lots of evidence of storms striking up to 15 kilometers ahead or behind itself. And so it happens enough that that's where that, some people have heard the term bolt out of a clear blue sky, that, there's nothing above you, but there's lightning. And where did it come from? And that's because it's a storm 15 kilometers away. It's certainly rare, but it happens enough that they talk about it. So if you're within 30 seconds, you're actually within 10 kilometers of that storm. And so it's well within that area of lightning, okay? So 15 kilometers takes about 45 seconds for sound to travel. So that's a good idea from that perspective. So within 30 seconds, you should be heading, and then you're off. And that's just because we always think about storms, you're off for 30 minutes, because we think about storms as, here comes the danger, but now the storm's past us and the danger is over. But the danger is actually not over, because the storm doesn't care whether it's shooting lightning ahead or behind. We always think about light storms always shoot ahead, but it actually shoots behind, just as statistically possible. So yeah, so you're sitting on shore for 30 minutes. It gives you plenty of time to come up with a good story about the whole thing. Make sure you can really hype it up, kind of like a good fish story. So, and then someone pays attention to the clock and you're off for 30 minutes, and then you jump back on when you're done. Okay.
Dave.
Yeah.
So we do have a couple questions here that I just wanted to get to before we got too far off of them.
Awesome.
There's one, it's going to go back a little bit here, but it's, do you know what causes the multiple storms? So when you have a front system or high-low pressures where you have that multiple storms coming in one after the other within like several hours?
Yeah. I do know. Do you want me to answer it?
Well, I think they would like you to answer it.
So it's exactly those boundaries of air where you have warm, moist air and cool air moving in, and that boundary is going to get a storm. And so on paper, we think about a single storm coming in, sweeping out all that warm, moist air and replacing it with cool air. But we know that temperature is gradient. So there could be something that could be super warm. Something that's coming in that's several degrees cooler with that is enough to cause a big storm right in between. But right behind it is cooler air even again coming in, and that boundary is big enough to cause another storm right in between. So rather than a huge jump of say 10 degrees, you might have a bunch of different air masses at different temperatures moving in. And that's one factor. There's a couple other things that could be a factor in it, but that's one that it goes from 30 degrees Celsius to 25 to 20, and you get these jumps within that. If you still have enough heat and moisture, the next thing coming in is what could be enough to kick it into another great storm. Does that make sense?
Thank you. That does make sense. I'll check the comments, see if there's anything else on it. That's fine. It sounded convincing. So why is a cave not a safe place for lightning to hide it?
Such a good question. Let's go back. And I only realized this a couple of years ago. We used to make fun of it. And the reason why, because you think, let's just run into a cave. It's because there's cracks in the rock and there's a lot of moisture in caves. And if lightning strikes here, the lightning can run through a vein of water that comes down and you can get electrocuted. Yeah.
Fun times. And going on that, that's another thing, since a lot of us do paddle in Algonquin Park and Temagami with the granite and the Canadian Shield. That's why if you ever find yourself in a lightning storm, you also want to be super careful of what you're sitting on, and you want to make sure you insulate yourself, because the lightning can run across the top of the rocks for the same reason.
Yeah. Lightning always wants to find the, it's looking for when it travels, it's always looking for the least objectionable path. It's always going to find the path of least resistance. That's a better correct term for it. So, it's going to run down a tree. This leads to the chaos factor, because it's going to run the outside of the tree that's covered in water down the outside, but then it could jump into you, because if you're leaning up against that tree, you might be at that millisecond, you're a better decision for it, and it could travel through you and keep going, or it could run across rocks or puddles. Like it can do all kinds of really interesting things. Scary things, so I don't want to dwell a ton on, lightning's one of those ones that we tend to fixate on as a fear thing, but it's risky. But in the grand scheme of things, it's a rare occurrence, thank goodness, but the thing is, the bigger message that I'm trying to, like, there's not good places to go, but the big thing I'm really trying to stress is that it's pretty predictable. Hot, hazy afternoons is going to lead to thunderstorms, at least here in like the Midwest area, or, you know, Ontario area. Get these really big days. So you should be thinking, you shouldn't be surprised when these big storms come up. We don't get thunderstorms in the winter, very, very rare, because there's just not enough moisture in the air to create that static electricity.
Awesome. Perfect. And then going on that, Jane has a question here, which is, how far does lightning travel if it hits water in a lake? And this one's a fun question because it has so many variables, from salinity to mineral content to the power of the lightning. So I don't think there's a hard number. Dave, do you know if there is kind of an idea of what the travel distance is, or how much
I was
it's gonna
reading
hurt?
about it just about a month ago because I actually couldn't remember. And from what I found is, it depends obviously if it's saltwater or not. But generally freshwater, it doesn't travel very far, which is part of the reason why the fish all don't get killed. It only goes, apparently, like, it tends to dissipate, unless it's going to go straight down and hit bottom. It tends to dissipate within like 50 feet. Like, it's actually not huge from that. But the fish that are in that range, they're not having a good time. But it's not a case that on the other side of the lake, it's going to strike and it's just going to kill everybody in the lake. It doesn't. I'm sure there's good examples of it somewhere, but statistically, it doesn't happen very much. The big factor in why we want to get off water, lightning striking you is a factor, but the more practical aspect to paddlers is the wind. You know, getting hit is not a good thing, but really, you want to get off the water because it's so chaotic, because the wind's blowing, it's screaming in your ears. You're going to have really bad high winds. You're going to tip over. Your friends are going to get blown all over the place. So getting off the water keeps you safer from lightning. But really, it's just chaotic. I've been in the middle of a storm where it was everything but lightning. And it's just like all of a sudden everyone's blowing everywhere and it's total chaos. And you really you don't want to be in that environment. It's just as dangerous as lightning is.
Yeah, exactly. And I think that's the biggest thing for us to realize, and that we like conveying, is the safety part is, if safe, get off the water, get into a safer position. And that goes to Bonnie's question about wearing rubber shoes, rubber boots, rubber things. Insulating yourself from the ground will always be a benefit. However, if you're still standing tall, you're still a higher risk. So there are positions, there are methods. Look up lightning position. I'll see if I can find a picture. I don't think I've seen one with David's presentation, but there are ways to do it to help yourself and make yourself less likely to become either hit by lightning, or what's the more, I'm going to use the word common, but it's not, when it does happen, is like Graham's put in the chat, is lightning runs across the ground and gets you.
Yeah.
So you want to insulate yourself from the ground.
Yeah, and the thing is the more they've learned about lightning, the less they know about it. It's super unpredictable, just because of that, the path of least resistance. Just there's that chaos factor, and you really can't figure out where it's going to go. There's places where it'll tend to go, but not always. Okay.
Exactly. So moving on.
Let's talk a little bit about wind. Windy wind. Okay. So I thought I'd just chat just really briefly about, for paddlers and thinking about wind, because there's some ways that we can make our life a little bit better, or it's along the line of trying to figure out why is the wind doing what it's doing. And that's kind of the angle here. I've got probably 3 or 4 slides, then we're going to be done. So wind, the way that wind flows around objects, across the water, across cliffs, around bends, it performs very similar to the way water does. In the sense of the fluid dynamics side of things, they're actually very similar properties in that. And so you get turbulence, you get really wind that blows in irregular patterns, and all these things happen. So if you think about how would this perform in water, wind does the same, is very similar way. So you got wind that's blowing offshore. Give me just a sec. Everyone's yelling here. Hold on a sec.
The joys from working and presenting from home.
Kids. In my day, I never interrupted a presentation on Zoom. All right, so we have, let's talk a little bit about wind and how it affects against shoreline. And so if you're paddling along this big cliff here, there's a tendency for us to say, okay, let's get really close to the shoreline and paddle along this cliff. But the way that wind blows over the cliff and out to sea is that right below the cliff, you get a little bit of a shadow that tends to be right in close to it, but you get a lot of turbulent water, turbulent air right above you. So sometimes when you're paddling, you're better to get way offshore, a couple hundred feet, half kilometer, where the air is more stable and blowing in a regular direction than you are really close to shore. Sometimes shore, in particular cases like this, sometimes shore can be more turbulent and windy or choppier than it is farther out. So it's just something to think about depending on how intense the wind and how big of a drop this thing is going to be. Okay. So we tend to want to tuck in really tight, but sometimes you're better to get farther out because predictability in wind and waves is easier to manage than it is turbulent side of things. When you're going around a headland or a big sticky outy thing that you're going around, you get lots of really interesting wind patterns right at it. And it depends on whether you're going against the wind or you're going down the wind. And right at this zone right here in the middle, if we think about what happens to water when it squeezes through its small thing, well, it speeds up significantly, and wind does the exact same thing. So if wind's blowing along the shoreline, some of it will go up and over, but some of it has to bend and go around it. And so because now you've got this constriction of wind that's blowing straight across, but now it's got to accommodate this wind to get around it, it's going to speed up significantly. And so that's part of the reason when you read stories of different incidents that's happened on the water, they tend to happen at big sticky outy points. And this is one factor. Sticky outy points tend to be shallower because of the erosion from the cliffs and things like that. There's a lot of rocks kind of right in that section. So it even magnifies it. So you got wind blowing across it was deep water and is now shallow water. So you've got faster winds and bigger waves. So essentially everything that happens in front of a big sticky outy point is just magnified even more. So when you're out with your buddies, it shouldn't surprise you when you go around the corner and all of a sudden there's a lot more wind because exactly what's happening is constriction flow around it. Okay. And then the same thing happens. This is an upper view of it coming down, blowing between two hills. And so here in Ontario, we don't have the same topography, but where wind comes through, you could be, if you're paddling along this stretch and you're in the shadow of it, all of a sudden you've got a valley, you're going to get some strong winds. I'm going to talk about winds and valleys in a second real quick, but you shouldn't be surprised when you look over to your right or to your left and you see a valley or you see a gap in between the hills, and all of a sudden it's going to get real windy. So you should think about that, especially late in the afternoon where the land is heated up, has heat up more than the water, and so you get a lot of afternoon winds and that type of thing. So as you can see in these examples, it's like sometimes we think the better place to be is closer to land, and sometimes you're better to just kind of get out a little bit farther where you're in that zone between. You don't want to get way offshore, but you don't want to be super close to shore because there's the chaos factor within that. And wind is an interesting little beast. The other term we talk about is channeling and funneling. And if you wanted to paddle up this little stretch here and the wind's blowing in against you in this direction, it's going to flow along the path of least resistance. So sometimes it's going to go over this big headland here, Killbear up in Parry Sound area, but sometimes it's going to flow around, and sometimes it's even going to flow up through these little channels. So when it flows through those areas and it gets constricted, what happens to the speed? It jacks up quite a bit. So if you're paddling along against this and you're thinking, okay, this is going to be perfect because I can hide out against this because the wind, you think the wind's just going to blow over you. Well, actually now all of a sudden you've got a really strong headwind because it's flowing around the passage of the land, and it's even faster for it. It's just fact of life, you're going to have to deal with it, but it shouldn't surprise you a little bit. So you kind of got to think about, where's the wind going to flow? If this was water, where would it flow? And it kind of makes a little bit more sense. So now when this one little micro area where the wind is, say, blowing kind of out of the southwest, it's actually blowing out of the northwest. Yeah, in this particular piece, just because the land is forcing it around that corner. So channeling and funneling, the funneling is it's squeezing through this area, and channeling just kind of runs up through channels. It's kind of the easiest way that I came up with, the only way I could kind of remember the two of those pieces. Okay. And oh, look, it's even labeled for us. And then wind also acts really strange around objects in the middle. In the middle of an object, and so the water is the same way. If you've ever worked in some moving water situations, along the outside of it, it gets that same type of where it squeezes past a headland. The same thing happens here. So wind blows against an island, and if you're paddling with like say if you're paddling with the wind and you need to get around this island, there's lots of times where the side of the island, all of a sudden the wind gets really strong, and that's just because it's splitting around, going around it, dealing with the wind that's already there, and it compresses and accelerates. So if you were going in the opposite direction, when you come beside of an island, especially if that island is close to shore and now there's a channel that you're going up, it's going to get really strong right in that one little stretch. And then if you think, okay, as soon as I get past this island, the wind is going to drop off 15%, and it does. Okay, well, it could be 20, could be 50%, but it drops off when you get ahead of that island a little bit. What's interesting about this is that when you get to the backside of this island, like water flows around it, it's going to backfill. Wind does the same thing. It'll go right behind that island, and on the backside of that island, depending on how intense it is and how big this island is you can get really choppy water right on the backside of that. So there's a tendency for us to say, okay, let's take a quick break right here, really close to these rocks, and then we'll get it around this point. Well, it could be really choppy right there. So sometimes you're better off to, instead of being right by that X, you're better off to like move farther out just a little bit where the wind is more predictable. You don't get that choppy mess for it. So going around and going up through islands and channels, it does, it's an interesting, weird things happen. Okay, and it's just really just the wind's interaction with the land and the water and the topography around you is kind of how that affects it. Okay, my last little piece is what's called anabatic and katabatic winds, and this is a much bigger factor in areas where you have high topography, so really tall hills and valleys. So you get this. We don't tend to get this to the same, we get a little bit here in Ontario, but we just don't have the hills, so we don't see it a whole lot. But certainly if you're paddling on the ocean where there's high hills or valleys, yeah, you get these types of things. Essentially what ends up happening is it's wind that travels in very predictable patterns. In the morning, it blows down a hill and out to sea, and in the afternoon, it blows back up the top. And they're just, the two names are anabatic and katabatic. So what happens here is the sun heats the land up, and what happens to the warm area, it rises and it goes up the hill. So you've got anabatic winds, so they blow inland and up the hill because of the rising. And because of that rising heat, the wind comes in behind, and so you get the cycle because it's coming around. So, but generally for us at the water level, it's blowing up. It looks like it's blowing uphill, but it's blowing up the valley. And then later at the night, the reverse happens because it cools down. So the land cools quicker. So all that air starts to blow down, the cycle reverses itself, okay? So here's kind of a quick example of what happens. And so you've got an inlet here or a fjord, and it doesn't need to be really big. It could be a couple hundred feet, and you're gonna get this effect. And so later in the day, as things start to cool down, you're gonna get this big draft of wind that blows through. And in some areas, it's very predictable. Like within 20 minutes, every single day, the same thing happens. And in the morning, the land starts to heat up kind of mid-morning. All of a sudden, you get this big gust of air that comes through and blows up the hill. Why is this important for us as paddlers? Well, a couple things that happens. If you're going to cross this valley or this fjord here, or you've got this crossing, you got to think about this, especially when you're in a mountainous area. What time of day is it? And what's going to happen over the next half hour to cross that over. And so you kind of need to be prepared to think about that one factor, especially this gets compounded if the tide is moving in and out. Say if you're on the ocean, well, obviously you're on the ocean if there's tide moving in or out. So if the tide is coming in while these winds are blowing down against that tide, you're going to get huge, giant waves. If the tide is going out while the wind is blowing down, you're still going to get waves, but not near as big. So there's a couple things that kind of roll in your head that you start to think about when you've got hills and you're paddling next to hills, especially late in the day. You could have these big winds that blow out. And then if you're in a situation where there's current current because of the tides, then that all of a sudden the waves get really big. And 20 minutes later, the whole thing is done. It's a really interesting little phenomenon. So they're called anabatic and katabatic winds, and I could never remember the fancy name between those two. And the only reason why I can remember it is because a cat jumps down from something up high and jumps down to attack somebody. So katabatic winds blow down the mountain like a kitty cat does, or a tiger. It depends on how exciting you want it to be. Okay. Well, I've experienced it a couple times in at a much smaller level on Lake Superior, where there's big hills and there's valleys, and all of a sudden it starts to blow down. And you're trying to figure out where did this wind come from, and that's exactly what's happening here. Okay, I'll leave you with this, guys. My last slide, and this is everything you need to know about the water cycle. There you go. Any questions that people have?
Thank you, Dave. Yeah, there's one question that Catherine brings up, and it's kind of goes into a bit of an old saying that people have used, and Tammy kind of got into it as well. Is there a safe distance to be from a tree or a danger point? So Tammy brought up the cone of protection, which is a term I haven't heard in a while.
Yeah, I heard it. I heard it described in the sense of somebody talking about staying under electrical wires with the same idea. Was there more to the question? I cut you off there. Sorry.
Yeah, well, the question mainly is there something, and it's the cone of protection is definitely, it's an older term I haven't heard in a few years now, and it's debated and mostly been debunked because it's so dependent on your environment you're in. Where are the tree roots? What's the granite? Is it granite, sand, salt water, fresh water? So there's so many factors into lightning safety.
There definitely is. And the other big thing that factor in that is how wet is that tree? So how much water is running down that bark? So is that electricity going to go through the trunk or down the outside of the trunk is another big factor in that. I mean, I remember my outdoor ed teacher years ago talking a little bit about that. He's like, he said, you're either going to get lightning running down the tree or it's going to blow a branch off you and it's going to hit you in the head. So that's kind of, I mean, he was obviously oversimplifying it, but I don't really know a good answer to it. There's, like he said, it can get debunked and some people believe in it. And I think it's just one of those things that it doesn't matter how, it's too chaotic to be able to come up with set rules. And it's like, even the way that we describe it is like, there's bad places and less bad places. Like they're all bad places. Generally a storm is like the worst thing you could have. From that
and that's one of the ones I've found. The lightning storms, they can be very deadly, very dangerous, and definitely something to watch out for. But one of the things I've seen almost more commonly is the microbursts.
Yeah, for sure.
That Algonquin Park back, 10 years ago, got slammed by them really hard. And a microburst is a reverse tornado, for simplified terms. It's a mass rush of air comes down, slams into the ground, and spins out. So I've watched it. We were at a campsite next to it. A campsite about 100 meters from us got hit. This microburst hit. It took an oak tree, spun it around itself, and detonated the tree and leveled several. And these things can be because there's zero warning to them. And that type of stuff, high wind, and seems to be a more likely danger factor that we're going to experience on common.
The greater the difference in temperature between both sides of the boundary, more degrees. So if that thing is going to drop 10 or more degrees, there's going to be a huge storm in between that. There's so much energy to transfer to go from 30 degrees to 15 degrees. It's only a massive storm that's going to deal with that. So it's it's an interesting thing. We tend to always want to dwell on the worst case scenario for things. And luckily, lightning, like I said, is one of those things that doesn't happen a whole lot. I mean, people get injured significantly more other ways when they're out camping than they do about lightning, and don't tend to think about it. I mean, burns on camp trips is way more common. So I don't want to, I try to always encourage people. It's like, it's a kind of a thing that happens. And so there's ways that you can mitigate it. You can't eliminate it. And so you kind of got to, if you want to go out, you kind of got to accept the risk of, how much risk can I take or willing to take for it. And so we're going to mitigate as much as we can by getting off the water, getting into the trees, avoiding some of the bad places for it. And that type of thing is kind of how we try to mitigate it. But the risk is still there. No doubt about it.
Yeah, for sure. And that's where, just so on the last point of lightning before we move on, just checking the questions, is Brad actually brought this up, and it's something interesting. Trees can explode when hit by lightning.
Yeah. They
Trees can,
boil super fast. They're
yeah,
cool.
and they can detonate. And it's kind of the same thing in the wintertime. Trees can also, you can get a section blow out of them because they freeze.
Yeah.
So it's kind of interesting that trees are they like exploding randomly on
I mean,
things.
the real message is just stay home. Don't leave your house. No one's ever died on a sofa. That's the place to be.
Clearly, but all of us would never follow that advice. Bonnie has a question. It's a stat question, and I'm pretty sure if you know this off the top of your head, I'll be amazed. But we never hear about people dying from lightning. She's like, how many people die by lightning? And I think it's going to be the same stat as like sharks,
It's
like 4 to 10 a year.
it depends where you, it's much higher than that, but it depends on where you are. And here in Ontario, kind of Midwest, like Great Lakes area, is it's not super high, but it's high enough that it's important enough to talk about it. But if you're in a place like Georgia, in the deep south where it's very high humidity, lightning is a big concern for those guys, and it's a big enough concern that people who work in the outdoors, like groundskeepers, golf courses, working in that, it's a big enough thing that they have government programs so that people carry lightning detectors on them. It's an actual significant workplace hazard in that place. There's these interesting lightning detectors that a lightning sends off an EMP or an electromagnetic pulse. So you can set these little, looks like old beepers, and you kind of set it for how sensitive you want it to be. And as soon as it goes off, then people are like, there's a storm in the area, and they have a protocol to head in. Kids soccer is a big enough thing. There's always a couple stories every year of some lightning that struck a soccer field. But yeah.
Yeah, so big thing is lightning is dangerous. That's something. Weather is spectacular, amazing, scary, dangerous, all at the same time.
Yeah, like a lightning storm is awesome when it's happening at the other end of the lake and you can watch it. That's the best thing.
It's great when it's not over top of you.
Oh, yeah.
Can you go back to your cloud slide?
Yeah.
The first one there that shows all 3 elevations, because we have 2 questions on clouds. We have one question, which is how can you tell how high a cloud is in the sky? Okay. That's kind of why I'm asking you to go back. And the other one is Dot has a question. What clouds give a hint that there will be rain tomorrow? Mirror tails, or mackerel clouds?
So essentially what you get here is judging the height of a cloud is really just kind of experience. And if you were to step outside and look at clouds, if it's, light now, you could probably make a good guess. This is high, medium, or low. But again, this is kind of super fuzzy. It's not, they have kind of distinct from like a scientific perspective, but really things are kind of super fuzzy. But generally the wispier the clouds, the higher they are. They're at the top of the level. But if we think about the transition, it starts as the wispiest type cloud, then they start to clump together, and then they clump together so much they turn into sheet-like. And as this is all happening, they're clumping together, but you're probably actually not seeing the height difference because that thing is so high up, it's 6 to 10, 15 kilometers above you. So you're not going to be able to detect the height level like that. But if you came back 5 hours later, you would see a difference if it was continuing to lower. So for people who are kind of new to it or kind of wanting to make a guess, you can make a rough guess whether it's high or medium. Low is easy because it's just like clouds are, right there. But as soon as you pay attention and watch it over a day, you would then see the noticeable difference between how clouds drop. Does that make sense?
That does make sense.
Yeah.
And I think a good thing why I wanted this picture was to give an idea of where the geese fly, because a lot of people don't realize that the geese fly really high.
Yeah, until they're like, trying to get on your beach or something like that. But yeah, this would be, so planes are at the upper, at the way upper level, and they want to get into that upper thing because they're clicking into the trade of the jet stream at this upper level. And so then geese are flying. This would be like if you're long distance hauling geese, they are the same way. They get into this level because the winds are stronger for the direction they want to travel in generally than they are at ground level. So, but yeah, it's kind of an interesting, clouds are, there's a ton of books you can buy on clouds, and there's tons of video that gets into like, this always means that. And but I found that when you really boil it down, you kind of the high, medium, and low seems to work because it's all, like I said, it's all about trends, and grouping together in trends is more important for it. Yeah.
Yeah. No, and that definitely makes sense. So there's a bunch of questions that just came in, so I'm just going to work my way through them. Bonnie, rubber water shoes really don't help because as soon as there's water in them, they're just as conductive as anything with water on it. So it's one of the things, just be aware, wet water shoes become conductive again. So that's where, going into that, we can go, oh, that's a good picture right there. I'm going to share my screen here just because somebody's asked about lightning position. So if you are ever super stuck into massive lightning storm or something coming in, this is a lightning position which you won't be able to maintain for very long because you're literally just standing on your toes with your heels together. And what happens is lightning, if it does hit the ground, runs across a root, runs across water, it enters one foot, goes up, goes across your heels, and then leaves on your other foot. So what it is, it's to minimize the passage of lightning through the body, because as we all know, our heads and our hearts do not like electricity. And the rest is just really going to hurt. So one thing, this is one position you can go with. It's even better if you have a pad or something. This is where your thermarest, your pad, your sitting pads are really helpful to add another layer of insulation. And since this position is so hard to maintain for long periods of time, the other one is the sitting position. So it's pretty much you just drop your butt down and keep your heels and feet out in front of you. Your heels are still together, your butt's on the ground or on your pad, and your feet are together. So now if lightning does come in, it's going to hit you, maybe your hip, and leave at your heel. The biggest thing is it stays away from your torso. One thing you will notice is the hands over the ears, because if you do get a really powerful lightning storm come in, the thunder from it can be a real shocker for people, and it really does throw people off, and it can damage hearing if it does strike really close. I know there's a few of us on this call who have been caught in thunderstorms with lightning that has hit pretty close, and close lightning, very loud. So that's lightning position. Great safety position to at least understand. Really useful if you have a storm right overhead. One of the things to watch out for is people like staying in their tents. Not always the best idea because you're in a giant metal structure. And they have in the past been hit before. So that's something just to be aware of. Dave, do you have anything to add to that?
Nope, but I saw Aaron's question here about other type of things. So extreme heat, I'll go the same thing from cold. Um, so the other weather conditions that can also be dangerous. The nice thing is things dealing with heat and cold, those are slightly easier to mitigate based on choices that you can make as far as clothing. How much clothing, or should you be out on the water that day, or if it's getting too hot, should we go and take a nap and then get on the water later today? Luckily, things like that are, when you kind of think about it, they're easier to mitigate than the extremes. They are dangerous being out and super cold or super hot, but they can there's things we can bring to mitigate from that perspective. Todd had a question around weather apps. Oh, there's a million of them out there. The big one that I tend to float around right now that I really like is Windy. Windy, Windy. It's just great. It's a really good package of stuff that gets super nerdy for me, but then you can switch over to a simple mode that's great for you guys. Well, not you guys. That sounded really condescending. I apologize. But for people who aren't interested in kind of the science nerd things. So that's the one that I tend to, but ultimately at the end of the day, the one that you are going to use is the one that's great when you really think about it.
Yes. So there are, just with the app. So I use my radar, and I prefer it because the alerts it gives me. But they're the same thing. Windy, my radar, the weather network, my weather. They're all very similar. It's fine. The one, like Dave was saying, that you like, you enjoy, and you'll use.
Yeah.
The official ones, if you want to know what the lakes are doing, is Environment Canada or Department of Fisheries. Which one has it there, Dave? Buoys.
Environment Canada.
Environment Canada. You can actually pull up the buoys off the lakes to figure out what the wind, the waves, and the weather is on the lake.
Yeah. And that's, I'll end it on this one. So if you're just the difference between a land forecast and a marine forecast, and it's just kind of just good information. A marine forecast. So if you find yourself on the ocean or the Great Lakes, you'll find a marine forecast as opposed to a land-based forecast, and it tends to be more focused because it's made for commercial industries. So people who are out fishing, like in a fishing boat, a commercial fishing boat, that's their real bread and butter market for that type of thing, and they're making forecasts for them. And those guys don't care about whether it's going to rain or not because it's just going to rain. Like they're going to work no matter what. But they're very interested in wind direction, wind speed, and wave height. Is the big thing that they're going to do. So there's lots of marine forecast. If you can get a marine forecast, whether it's on a VHF radio or get it from the internet, it tends to focus on the things that we as paddlers really want. Now, they don't have it everywhere. So if you're inland somewhere, then these factors don't affect you to the same thing. And a land-based forecast will work just great. But that's the big difference is fixated, not fixated, it focuses on wind as its primary source, really what's happening from a wind perspective. Temperature and rain as just extra information for them. So
awesome.
Yeah.
So I'm going to say thank you, David, here. If people do have any extra questions or whatnot, please stay on. We'll leave the call open for a little bit longer to help get through any questions or comments you guys have. Two things I do ask: if you do have any feedback for the presentation for Dave or his slideshow there, please let us know. And you can email National Paddling Conference at gmail.com. And then any of the feedback I get, I'll make sure I pass on to Dave there. One thing I do want to let people know about that is happening in 30 minutes. And because it is an exclusive screening event that people may be really interested in, is Track Kayaks is putting on, what is it, a 4,400 kilometer exclusive screening of one of the Mongolian, the Amur River, which travels from Mongolia through Russia to the Pacific Ocean. So it is an event that is happening at 9 o'clock our time. It's supposed to be about 30 minutes. The link is in the chat if you are interested in that. That does start there. And mainly I'm throwing up there because it looks super interesting, so I'm going to attend it. But yeah, so again, we thank everybody for coming out. Thank you for registering. Any feedback would be great. Any other questions, please let us know. Feel free to email us questions as well. We can help work through it. And with that, thank you. And thank you, David.
Thank you. That was great. I'm so glad you guys came out.